This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
Standard physics treats reality as a collection of isolated particles acting on a fixed background. The monopole theory of everything starts with a different premise. Its dynamics generate lab-measurable properties like emergent mass, effective mass scale, and energy density. The monopole is no longer a hypothetical particle. It acts as an ontological selector. Its presence perturbs the surrounding field, and that perturbation dictates whether a specific branch of physics is stable enough to exist. We can trace the origin of magnetic charge to the classical Dirac monopole. Dirac modeled this as an abelian U1 singularity. U1 refers to the continuous mathematical symmetry group governing standard electromagnetism. To mathematically describe Dirac's monopole over an entire sphere, you cannot use a single smooth equation. You must divide the sphere into overlapping northern and southern coordinate patches, connected by singular flux lines. Physicists resolve this using the Hooft Polyakov model, which relies on broken gauge symmetry. This model eliminates singular flux lines, mapping the solitonic core outward with smooth asymptotic lines that extend to a surrounding sphere, terminating in the vacuum manifold. This reveals a strict rule. You can have two field configurations that yield the exact same local energy densities, but if you zoom out, they might belong to completely different global topological classes. Smooth local fields do not guarantee a stable reality. A reality sector's existence is defined by its global topological class and sector memory, the permanent invariant data stored in the field's macrostructure. To calculate how topology couples to observer limits, the theory uses a classical coherence field. This equation is the prototype coherence Lagrangian, isolating the self-potential term. This chart shows the term's landscape, establishing preferred coherence amplitudes. Plotted minima represent stable sectors. Peaks and barriers denote metastable regimes. By applying an Euler-Lagrange variation, a calculus method used to find the mathematical path of least action, we determine the background coherence dynamics of the field. The variation identifies a stationary point. This point serves as the background solution, anchoring the candidate reality sector in a mathematically stable state. A common theoretical misstep is taking this first-order field equation and attempting to build an effective coherence operator directly from it. The first-order background solution only supplies the classical consistency equation. It lacks the mathematical rigor required to evaluate realizability at the quantum operator level. The framework corrects this through the operator delay principle. This rule mandates that operator theory begins exclusively at the second order of derivation. To reach the second order, we perform a Taylor expansion of the coherence action, mapping it around our established background solution. A Taylor expansion is a method that approximates complex functions using an infinite sum of polynomial terms. We extract the quadratic fluctuation term from the expansion, which resolves into the formal Hessian operator equation. The Hessian operator provides the exact mathematical rules for linearized stability. It dictates how nearby microfluctuations transport through the field over time. To apply rigorous spectral calculus to the system, the field must be established as a positive, self-adjoint operator regime. This means its eigenvalues are real and its energy states are bounded above zero. Once reduced to this positive state, the fluctuation operator functions as the stabilized transport backbone for the entire coherence observable. Measuring the static background sector is insufficient. Physical realizability is stabilized by rigorously measuring the small fluctuations around that background. The second variation is the gateway to observable physics. This brings us to the complete effective coherence operator equation. It serves as the central evaluative tool of the theory, arranged in a distinct three-part structure. The central variable is the smeared topological source observable. This term injects the specific monopole defect density into the calculation. Smearing distributes a theoretical point charge over a spatial volume to prevent mathematical blowups. The equation relies on a structural sandwich mechanism. The raw topological data is mathematically filtered through the bounding bracket matrices, which represent the positive fluctuation backbone. The final variable is a bounded positive operator that encodes the observer sector admissibility constraint. This final operator enforces projection compatibility, acting as a strict mathematical filter, preventing dynamically possible but unobservable sectors from existing. Empirical reality is an exact sum. It is the topological defect density, transported through a coherence response and weighted by strict observer admissibility. When we scale these quantum operators up to macro-scale cosmological dynamics, the background coherence fields begin to modify the macroscopic evolution of the universe. This requires an update to the standard FLRW expansion equation, which describes the metric expansion of the universe. Here, the traditional cosmological constant, lambda, is explicitly crossed out. Lambda is replaced entirely by terms representing the average topological defect fluid and macroscopic coherence gradients. These new geometric drivers organically produce the accelerated expansion we observe in the universe. The framework accounts for dark energy-like behavior without relying on a rigid, unexplained vacuum constant. This architecture also forces a reevaluation of cosmic singularities, like the Big Bang or the centers of black holes. Physical reality is not literal physical infinities where matter condenses to a point. They are projection degeneracies, the specific boundaries where an observer-compatible projection regime mathematically breaks down. The effective operator ultimately produces a single scalar output, known as the stabilized coherence score. This score feeds into the Boolean realizability predicate. The inequality equation acts as a final decision surface, evaluating the quantum state vector against a hard numerical threshold. If the calculated score falls below that threshold, the branch fails. The state vector dissipates, deemed physically inadmissible. Physical reality is not defined by whatever differential equations happen to permit. It is exclusively the set of configurations surviving the coupled coherence filter.